Alright, hey, it's Mr. K doing a problem for AP Physics 1. I'm going to be gone for the day. Here's the problem that you need to do. You have all class period to do it, and here it is. You have a disk. It is a solid disk. It's going to roll without slipping. That's very important, that it rolls without slipping all the way down to the bottom of the incline. I just drew this triangle. I measured the angle to be 25.87 degrees. That doesn't really matter too much because I want you to solve this using variables if you can. And this thing is a height of h initially. This will be L if you want to call it L. There's enough friction so it doesn't slip once again. And here are all the new equations that you might need to know. These three are just kinematic equations. And they are the kinematic equations for rotational motion. This guy over here is the kinetic energy of rotation. So if something's spinning, it has kinetic energy due to this equation right here. I would be the inertia of the object. Omega here would be how fast it's spinning in radians per second. This one right here, this is work. This is how we get the kinetic energy of rotation. That's going to be torque for a theta, kind of like force times the distance, but torque for a theta, because torque is going to be that twisty thing. Inertia is going to be mr squared for a point mass, where there's going to be like some kind of fraction up front. In the case of a disk, the inertia for this disk would be 1/2 mr squared, the mass times the radius squared of the disk. Right, this is the disk. Okay, and over here, this is called angular momentum. This is kind of like regular momentum, but it's you worry about where the mass is. Therefore, we need to use this term called inertia. And then omega would be the angular velocity. How you change it is torque for a time, just like how force times time is an impulse for linear momentum. Torque for a time will be an impulse for angular momentum. Angular momentum should be conserved unless there's an outside force, which in this case there should be an outside force. And then of course torque itself would be a force that is trying to rotate something, so you have to have that force applied at a distance away from a center of rotation in order to turn it. That's going to be that R. You got to make sure these two things are perpendicular. So you might have to take some components every once in a while. Here you probably won't if you do it right. And just like an unbalanced force is equal to ma, an unbalanced torque is equal to I alpha. It's going to get the thing accelerating. So your problem is to consider that this is starting from rest up here. It's going to roll down without slipping. It's going to get down to the bottom. And you got to find out how fast it's going to be moving at the end, how fast the translational speed is. It'll relate to the rotational speed as well, but just find out how fast it's translating down. You need to find the acceleration because it will speed up as it went down here. And you got to find the time to get down there. And so if you would solve that, that would be awesome. That's the problem, and I'll make another video for the solution.